E squared by 12 pi squared. E is the electric charge in CGS units. So, in field particle physics people normally use CGS units. So, it is not in Coulomb, but it is in ESU, and E squared by 4 pi is alpha, which is called fine structure constant. Okay. And fine structure constant is computed, is called 1 by 137 when your momentum is close to 0. Okay. It will become clear. So, in a minute. Okay. So, I can solve this equation exactly like what we did before. Okay. So, this lambda is okay, I should not, lambda is E squared. No? Okay. For electric thing, lambda E squared by 4 pi, I think I right now forgot, but the E squared is a coupling constant, is the interaction term, no, for two charged particles. What is the interaction term? E squared, no. So, the E squared is come here. So, exactly same logic, I get this. Actually, I may have a typo here, I think it is E cube, I do not remember right now. So, this equation I am slightly not sure, because I did copy paste here, but anyway, the running coupling constant we derive exactly same manner. What, well, I mean, derivation of this is complicated. Okay, this requires huge work, Nobel Prize for Feynman and Singer, okay, and Tomonaga. But this huge work, but once you have the beta function, I can compute how the coupling constant will change with momentum, and so that is the momentum. That is a running coupling constant. It is called running coupling constant, because coupling constant changes with momentum. Now, this is the experimental data. So, why this axis? Okay. So, x axis, this q is momentum. Okay. So, this is normally in particle physics, this q is called momentum. Okay. Now, it is two particles are coming, so it is a relative momentum, but we do not need to get too much into that. So, this is like p, okay, for what I wrote p is equal to m squared. I think I am making too many mistakes, m squared. Okay. So, this is a momentum. Now, when I increase momentum, my coupling constant is increasing, this alpha is the coupling constant, is increasing, okay, and these are experimental data. Now, if you go to very small momentum, then you will hit this line. So, suppose it will suppose hit that line, okay, and this line is 1 by 137. Okay. Of course, I think people have done a lot of work to get these 3 digits. Okay. Now, I will not discuss that, I do not know, but this is how you derive the coupling running coupling constant for QED. So, see that when you increase the momentum, my coupling constant is increasing. What does it mean? When I increase the momentum, that means I am going closer and closer to the electron. No? To probe the electron closer, I need larger momentum. When I go closer, then I see more charges. Okay. Now, what does it mean? Why should I see more charges? The reason why I see more charges is if I have electron, this vacuum is not free space. This electron will create lot of electric field, and that will create electron positron pairs. So, they creates E plus and E minus. Not electron positron pair, it also create quark anti quark pairs, all sorts of pairs. And which will come closer? E plus will come closer, E minus will come closer. Negative charge will attract the positive charge. So, E plus will come closer and E minus will go far away. So, it turns out effectively it is keeping some E plus closer, positive charge is closer. So, it is shielded when I go closer and closer. So, the shielding of charges when I go of electron because of these virtual particles, this is called vacuum polarization. Okay. So, this is vacuum itself is polarized like material polarization, vacuum is not vacuum like free space, it has all these properties. So, free electron, there is nothing called single electron. Electron will create lot of virtual the real particle, I should not say virtual particle, real particles which are pairs, particle antiparticle pairs, and there is always shielding because of this, these new particles will shield the electron. So, if I am too far away, then I will see less charge. If I go closer, then there will be less shielding, right. I mean, if you go meet the bare electron, that is infinite charge, huge charge. Okay. So, this is called I mean you do not go close to the electron, but this is what is a formula for the coupling constant. Okay. So, this is how we derive this charge renormalization. Okay. And why is it this called running coupling constant? Okay. This is running, is changing with wave momentum. Now, this for QED, what happens to QCD, quantum chromodynamics? That is even harder to compute this beta function. This beta function is even harder, okay, because it has quarks and gluons. Okay, that is you have to work with quarks and gluons, and it is definitely not easy. But we can write down, I mean this was written by people. This is the equation for the running coupling constant, which is very similar except a sign change. If for QD it was minus, for QCD it is plus. So, what happens is a plus sign. So, for large momentum what will happen? This m squared is it. What happens to large momentum? It will decrease, in fact become 0 for large momentum. So, you see that is what is happening to this coupling constant is going decreasing with momentum, and if you go to huge momentum then it will become 0. So, what does it mean coupling constant being 0? It has interpretation, is again one Nobel Prize. So, no force, the quarks are free when they are close by. Okay. So, the quarks do not, I mean put the two quarks together, they are happily sitting side by side. When you take them away, then it becomes harder. There is a force when you take them away. In fact, you cannot separate them as make a free quarks, because the force is increasing with distance, and it is apparent here. That is what it meant. If I decrease the momentum, that means I coarse grain of becoming larger momentum, then I am my force is increasing, the coupling constant is increasing. Okay. So, it is impossible to get a free quark. Okay. So, this is coming from, of course, the beta function computation is hard, but once I have the beta function I can compute this running coupling constant. Okay. For 5-4 theory is easy, well I showed you how to do it, we do that. Okay. So, this for the charge for the coupling constant. Now, I should also look at the renormalization of m squared, no? That is another parameter. So, let us look at m squared renormalization, running mass. Okay. So, this is my equation. So, here I get delta m squared, this is the formula I showed you. Okay. Now, this integral, the next step is easy, this one, right, it is exactly same, this omega d is surface area, but this one we want to do slightly sophisticated. We can write down as m squared is small. So, I write as m squared outside 1 plus k squared by m squared. Okay. I am going to do some approximation anyway, but so this one has two terms. Okay. I think so I will skip the algebra. Okay. I will just go to this integral can be easily done, but it has two terms, one coming from 1 over m squared, other coming from k squared. Okay. So, this will have d minus 1 dk, no sorry, no other way around, k squared is big. So, I should take k squared out, not other way around. So, I should take k squared is large. So, I want to do expansion, then I need to do that 1 over k squared 1 plus m squared by k squared. Okay. So, one is 1 over, so k d minus 1 by k squared, and I do the expansion, this is 1 over k squared 1 minus m squared by k squared, right. This goes up until expansion. So, other term is 1 over k 4 k d minus 1. So, two terms, and what gives you important contribution is this term. This term is small. Okay. So, this term is ignored in fact. So, I will not discuss this in detail, but this term is ignored, and the term which is d minus 1 minus 4 which is d minus 5, right. When I integrate I will get k d minus 5 dk, right. D minus 1 minus 4 is k minus 5, integrate I get lambda d minus 4 by d minus 4, right. I mean that is the integral. So, this is lambda d minus 4 will become 1 because d is near 4, and I get d minus 4, m squared is coming from here, and this is the term coming from lambda to the power lambda naught minus lambda, right. I mean this is their lower limit and upper limit. So, this coming from that lambda to the power lambda naught to the power 4 minus d or d minus 4 and lambda to the power d minus 4. Okay. So, this is the my correction. Okay. So, this bit of algebra, but I think we will skip some steps, we will just keep this term. Now, b again I expand is like e to power l, b is e to power l. So, this is log. So, you can write this as e to power l 4 minus d, 4 minus d is epsilon. Okay. So, this gives you that log b. Okay. Basically, it gives you L like before 1 minus this, what will that be? 1 minus 1 plus epsilon L, right. So, 1 cancel. So, this is epsilon L, epsilon will cancel with that and get L, and L is log b, this is log b. So, m squared correction is proportional to log b. So, I can derive the equation, differential equation. So, that is m squared, well now again we need to stop a minute, m squared decreases, we go to higher, smaller momentum, there is a minus sign sitting here. Okay. So, now I need to go to higher momentum. So, I need to change minus to plus. So, I just this sign I change it if I go from lower wave numbers to higher wave numbers. So, this become plus. Now, this can be solved. In fact, this is bit simpler, I mean this equation I need to solve. I will skip the steps and I write down the final answer. It is this, m square is m naught square plus this. So, this momentum mass is increasing when I go to higher momentum. Okay. So, this is what we get. So, we can see that both charges and mass for 5-4 theory increases with momentum. Okay. Now, I made a remark for QED without deriving the beta function, but okay, I mean, so this is how we do it. So, summary, in 5-4 theory charge and mass get renormalized due to interactions, both charge and mass increase with momentum or as we go to small scales. QED has similar behavior, okay, and QCD in fact is other way around. Okay, I did mention it. Coupling constant becomes small when you go to lower higher momentum, and that is it. Stop.